Now that we've looked at PID controllers and some ideas on how we might design PID controllers, we return to looking at some different properties of feedback control systems. And one idea that we've talked a lot about in different contexts already is the idea of steady-state error. And over the next 3 sections, we're really going to dig more deeply into steady-state error and how to quantify it and how to think about it in different ways and ways that might be helpful when we're designing controllers in order to be able to get rid of it and improve it. So system error is any difference between R and Y. So we calculate error of t equals R of t minus Y of t. So any difference for any reason between R and Y is error. There's 2 sources. One is because for whatever reason we're not tracking R of t well enough, even if there is no disturbance in the system. So our controller is just not sufficient to be able to cause that to happen. That will cause an error. The other is that disturbance is affecting the system's output. So if there was no disturbance, we might be tracking perfectly, but because there is disturbance, we are not tracking perfectly. So we're going to break down our discussion of steady-state error into first talking about steady-state error with respect to WRT, the reference input, that's type 1, and then after that, we are going to looking at steady-state errors caused by the disturbance, so with respect to the disturbance input. So section 4.7 and 4.8 both look at reference input reference input error, and section 4.9 talks about steady-state error due to the disturbance input. Both talking about the same thing, but different causes. Very easy to get those confused, though. In our journey so far, we've seen examples of closed-loop systems that have some tracking error. For example, the proportional control of our motor, or not, when we did integral controller of the motor, when we had a step-like input to the system. And we're going to formalize this concept here and also step away from that specific example of the motor and be much more generic so that we can consider any control system at all and how we would think about steady-state error in that case. So we're starting with a very general idea. A general idea is that I've got some system has a reference input I would like to track, and it has an output that is how well I am doing at tracking that. And in between is some transfer function, T of S. I say closed loop because I'm imagining that there's a feedback system in there, but there's just some transfer function that computes Y of S from R of S. We don't care in this section of notes what is inside that box, T of S. It could be any block diagram, and we may actually need to do quite a bit of work to compute T of S from the block diagram. But once we have T of S, then we can evaluate what its steady-state error is going to be with respect to the reference input. As we said, error is E of t equals R of t minus Y of t. So in Laplace domain, error of S is R of S minus Y of S. The transfer function t says, oh, I can compute Y from R, Y equals t times R. And then I realized that both of these terms in error have R common to them. So E of S equals 1 minus T of S all multiplied by R of S. If you think about it, this system has a transfer function from R to Y, but it also has a transfer function from R to E. And the transfer function from R to E is this 1 minus T of S. we're going to, when we're evaluating steady state error, assume that the conditions of the final value theorem are satisfied so that E of S has poles only in the left half plane, except maybe for a single pole at the origin. We'll use the final value theorem to say, well, what is the steady state error? So steady state error, by definition, is the value of the error signal as time goes to infinity. And using the final value theorem, it's the limit as S approaches 0 of S times E of S, and E of S is 1 minus T all times R. So this is our steady state error. This is how we compute it. We could think about steady state error to tracking any number of different reference inputs, but what is done in practice is to consider only a single family of inputs that we might want to track. And this family is chosen because the first member of the family is quite easy to track. The second member is more difficult. The next member is more difficult yet, and so forth. So by comparing our system behavior to how well it tracks these inputs, we can categorize the system in a nice way. So the type of input that we're interested in the time domain looks a little bit challenging. It's R of t is equal to t to the kth power divided by k factorial times 1 of t for different values of k, greater than or equal to 0, integer k greater than or equal to 0. And it looks ugly in the time domain, but in the Laplace domain, it's not so bad. R of s is 1 over s to the k plus 1. So for k equals 0, R of s equals 1 over s. For k equals 1, R of s equals 1 over s squared, etc. And we can draw the time domain equivalence of those. For k equals 0, the input we're trying to track is the step. Well, this is what we've seen all along. We wanted to track the step response of a system, and that is the easiest one of this family to track. For k equals 1, I'm trying to track the unit ramp. For k equals 2, I'm trying to track the scaled parabola, and so forth. So this is k equals 1, and this is k equals 2, etc. It just gets harder and harder because in the first case, I'm trying to track a constant. So it's not, the reference is not itself moving. So even if I wobble around a bit, I got a pretty good chance of getting there eventually. Well, in the next case, I'm trying to track something that's always moving, so I have to keep up with the movement and try to track that. In the third case, it's not only moving, it's accelerating, and then beyond that, it has higher moments. So it gets harder as k increases, and so this is why this family is nice to think about, is saying, well, I can track that one and that one, but not that one, and that then lets you think about things in a consistent way. This consistent way is the system type. This is a new concept. The system type describes the ability of our closed-loop system to track inputs of different kinds. And this is the definition here, basically, is if my system is of type 0, then it will track the step input with some constant steady-state error that's not 0. It won't be able to track the ramp or the parabola at all. If I have a system that has system type 1, what that means is that, in fact, I can track the step input perfectly. I will have some error when I'm trying to track a ramp, but I won't be able to track a parabola at all. If I have a system that's system type 2, then I can track the step and the ramp inputs perfectly in steady state, and then I will have some non-zero constant steady state error when I'm trying to track a parabolic input, and so forth. To find the system type in general, what we need to do is we need to compute the steady state error by trial and error for k equals 0, 1, 2, 3, 4, whatever, until we calculate some finite non-zero value for steady state error. So this is the approach. We say steady state error ESS equals lim as s goes to 0 of s times E of s. Well, that's equal to the limit as s goes to 0 of s times 1 minus t of s all times r of s. And then we say, oh, well, that's equal to the limit as s goes to 0 of s times 1 minus t of s, 1 over s to the k plus 1 for the type of r of s that we've said we're interested in. And then we notice that there's an s here and there's a bunch of them here. So overall, I am computing steady state error as the limit as s goes to 0 of 1 minus t of s over s to the k. And be careful with this. Remember that the limit has the lowest order of operation, so I do it last. So the fact that I see an s to the k power over here and s is going to 0 at first looks alarming because it looks like I'm dividing by 0. But in fact, there may be cancellations between this numerator 1 minus t of s and s to the k, and those cancellations must happen before I take the limit. And that's what causes these different system types to occur. So choose a value of k, compute this limit. If the limit is equal to 0, that means try again. The system type is bigger than the number k that I tried. If I get some constant non-zero value, then I have found the system type, and I have actually found what the steady state error is also. It's that constant value. If I compute the steady state error equals infinity, then I tried too large a k, and I have to try again with a smaller value of k in order to find the system type. So that gives us a procedure to follow. It's a little bit cumbersome because you have to do a bunch of these to try it out, but it still is not a bad, difficult thing to do. Here's an example of what system type looks like when I'm trying to track a ramp input. So the blue line in all three of these plots is the desired input. This is, I guess it's time domain, so it's r of t. Is the reference input is the ramp. And this here is y of t. If a type 0 system tries to track a ramp, it's going to try as hard as it can, but you'll notice that the error gets bigger and bigger and bigger as time goes on. And so in steady state, there's infinite error when a type 0 system tries to track a ramp input. When a type 1 system tries to track the ramp, you'll see that there's a little bit of a transient effect there while it's getting caught up. And in the end, that difference there is the same as that difference there. It never quite catches up to the ramp, but it stays a constant distance away, so it has a constant steady state error when tracking a ramp. When a type 2 system tries to track a ramp, you'll notice that there is some oscillation there around the reference value, but in steady state there is in fact no error because a type 2 system can track a ramp perfectly. So remember, we're talking about what happens from R going through T of S going to Y, and I said that T of S was just some box. It could be anything, and it could be the system with our controller built in, and so we might have some capability to design T of S because, well, we have a controller inside that box. So it sounds like we might want to design a T of S that's a type 2 system, or maybe even a type 200 system, because my goodness, if I could track a 200th order input, that sounds really amazing. But there's a danger here, and the danger is that the higher order sounds better, but they're much harder to stabilize and to design, and the transient response may be poor. So here you see some rippling. In this case, it's not too bad, but we might have very poor transient response just that in order to achieve the very, very nice steady state response. So design is always a trade-off, and here we would like a good system type, but we have to be careful. So I've put in a summary table in the notes here to help us think about how we would compute steady-state error and what that value of steady-state error would be. And in this table, we see, okay, the title is Steady-State Tracking Errors for Generic Closed-Loop Transfer Function. And if the system type is 0, and I give the system a step input, there will be a steady-state error. And this is what it is. And if I give the system a ramp input, it won't be able to catch up. If I give it a parabola input, even worse. If the system is type 1, and I give it a step input, there will be no error. And if I give it a ramp input, this is what the value of the tracking error is going to be. If I give it a parabolic input, it won't be able to do it. If the system is type 2, step input, no error, ramp input, no error, parabolic input, this is what the value of the error would be. Please put some kind of a note in your binder for this table, because we're going to have a very similar table in the next section, and it's very easy to get those two confused. So make a note, maybe highlight, do whatever it takes for you to be able to recognize that this table here is specifically for a generic closed-loop transfer function that we're talking about. When we get to the next section, we're going to be looking at a very special case. It's a frequent special case, but it's a special case, and so that table is going to look different from this, and I want you to be able to do both and to recognize when you need to use one versus the other. So make a mark, make a notation, whatever it takes for you to be able to come back to the right place. The rest of this section, though, we're going to look at some examples. I've kind of told you in words how to find the system type, but let's go through some examples to see it work out in practice. So, example number 1. Consider a closed-loop transfer function T of S equals S plus 1 divided by S plus 2 times S plus 3. What's the system type? Well, it's nothing to it but just brute force. Try k equals 0. We plug it into the equation. We say, what is the limit as s approaches 0 of 1 minus t of s? So you get pretty good at doing subtraction of polynomials. So if that's t of s, then 1 is equal to s plus 2, s plus 3, all divided by s plus 2, s plus 3 to have the same denominator, minus t of s, s plus 1 over s plus 2, s plus 3. And that's what I did to get this right there. You'll see that. And so I take the limit as s approaches 0 of that polynomial. And that's 0, that's 0, that's 0, that's 0, that's 0. And I get 2 times 3 minus 1 in the numerator, which is 5. 2 times 3 in the denominator, which is 6. Overall steady-state error of 5/6, not 0. Therefore, we can stop. We know the system type is a type 0 system. Why? Because I did this limit, and I found that it was not 0. Therefore, I have a type 0 system, and the steady-state error is 5/6 to a unit step input. Example 2. Consider T of S is equal to S plus 6 over S plus 2, S plus 3. Very similar to the first one, notice, but the numerator is slightly different. So what's the system type? So again, we try k equals 0, and we perform that limit. And we do 1 minus T of S, gives me the same numerator thing there. I'm doing this 1 minus, but this is different from before. And as s goes to 0, that 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 goes to 0. My numerator is 2 times 3 minus 6, which is 0. My denominator is 2 times 3, which is 6. 0 over 6 equals 0. Oh, okay. So I tried that equation for k equals 0. I go back to here and I say, well, I didn't get a finite number there. I got, in fact, 0. So I've either got a type 1 or a type 2 or higher system. So I have to keep on going. Try k equals 1. So now we evaluate limit 1 minus t of s over s as s goes to 0. The good news is I don't really have to do a lot of math over again. We've already computed all of this, so all of that gets repeated. What's new is this 1 over s. But I'm going to be a little bit more careful here. When I compute what's going on in the numerator, I'm actually going to multiply things out. So moving this over here, this numerator equals, that's going to be what? It's going to be s squared plus 2s plus 3s is 5s plus 6 minus s minus 6. So that's going to be s squared plus 4s is plus 6 minus 6. So s squared plus 4s, which is what we have here. Again, the limit operation has the lowest order of precedence, so this 1 over s is going to cancel this s, and it's going to cancel one of those s's. So my numerator is now s plus 4, and my denominator is s plus 2 times s plus 3. And when I take the limit as s goes to 0, that's 0, that's 0, that's 0. My numerator is 4. My denominator is 2 times 3, which is 6. I get 4/6, not 0. So going back to my table, I tried this. I got a 0. I tried this. I did not get 0. Therefore, I have a type 1 system. One more example. I'll let you guess what type of system it's probably going to be. Example 3. Consider t of s equals 5s plus 6, all divided by s plus 2 times s plus 3. Again, same denominator, I just changed the numerator a little bit. Try k equals 0. Take the limit as s approaches 0 of 1 minus t of s. And same idea, I've got the s plus 2, s plus 3, but the numerator is different. And here I've got, let me see, as s goes to 0, that's 0, 0, 0, and 0, 0. My numerator is 2 times 3, which is 6, minus 6, which is 0. Denominator is 2 times 3, which is 6. So I end up with a 0 result. I have a system type that must be greater than 0. So try k equals 1. Limit as s goes to 0 of 1 minus t of s over s. So same idea as before. There's the 1 over s, and the 1 minus t of s is the same stuff that we had, but I'm going to now multiply this out carefully. So my numerator equals, it's going to be s squared plus 5s plus 6, and then minus 5s minus 6 gives me s squared. That's what we have there. When I divide by s, I've got that s there, and the s squared just becomes s. And I substitute s goes to 0. The numerator is s, which is 0. Denominator is 6. The answer is 0, steady state error, to a ramp input. So we have to then go back to the table and say, well, I tried a step input, I got 0 steady state error. I tried a ramp input, I got 0 steady state error. So my system type must be at least 2, maybe it's more, maybe it's higher than 2. So let me try this parabolic input and see if I get a non-zero value there. So try k equals 2. So I say limit as s goes to 0 of 1 minus t of s over s squared. Same as before, except I've got a 1 over s squared there. My 1 minus t of s is what I calculated above. And now I cancel whatever I can before I take the limit. I've got a whole s squared. I've got 1 whole s squared there. So my numerator is now 1. My denominator is s plus 2, s plus 3. As s goes to 0, that goes to 0, that goes to 0. My numerator is 1, my denominator is 6, and that is not equal to 0. So I have a system type which is type 2, and I have a steady state error of 1/6 to a unit parabola input. So that's how you do it. It's fairly mechanical. You just keep on going through and trying higher and higher values of k until you achieve one that gives you a non-zero finite number, and that value of k is your system type. Where we're going next is a special case of this, so please solidify this in your mind first so that you understand the general case, but the special case has some important simplifications.